All right, we're live. Yeah, we're live. All right, well, hi everyone. Welcome to another Math Club meeting. I'm gonna put one of the board members here, and today we're having Professor Shah from the CS department talk about computational geometry. A few announcements before that though. Once again, thank you for joining. We're gonna have a social event on Sunday that will be painting
pumpkins and pie. We're painting pumpkins on the West Village quad, and we are going to provide pizza and pie.
Yes, yeah. So everyone's welcome. All Math Club members are welcome to join, of course. So that'll be at 1 p.m. Is that right?
Yep, 1 p.m. on Sunday.
Yes, if you're in the Discord, please react or like say you're interested on the invite, so we know how much stuff to
How much
buy.
pizza and how much
Yes, and how many pumpkins. So
And then next Thursday, we're going to have next Thursday at 3 p.m. It's going to be a course info session, a math course info session. So there'll be a bunch of professors. Where's that meeting at?
It's going to be in the next room over that direction.
110.
110 that way.
And so there'll be a bunch of professors here to talk about math courses. I'm sure for anyone, registration starting pretty soon. So if
We
you guys
already have 9+ confirmed professors who will be talking at that. Go.
Yeah, special thanks to Zach as well as Kane for organizing that event. But yeah, if you have any questions about certain courses, all the courses that are being offered next semester, stop by. There'll be food and we can talk about there. And there will also be
If you want to follow up on that one with a professor, if you don't have enough time to ask the questions you want, or if you want to talk to the professor further, if you want to take their class, the Thursday after that, we will be having a social in the math lounge to follow up on that, and all the professors will be there who went and read the presentations.
All right, so those are all the announcements for this meeting. I think later on, stick around after as well. I think we'll have an attendance form up just to do a quick scan and get that and keep track of how many people attended. But yeah, I'll represent Mr. Mike Shah. He's going to talk about computational geometry and enjoy.
All right, thanks, Glenn. Thanks everybody for having me in Math Club. This is super exciting just to see all the folks out here. Go ahead and open up some slides. So here's me. I will post the slides online on my website. You can just Google my name, Mike Northeastern Computer Science. You'll find me. I'll send these to you when more than that otherwise too. Just to get sort of a lay of the land here. How many folks are math? I guess okay. CS. It's about half and half for the record. And then I'm assuming some are combined math, CS, and some combination. All right, so most folks are math. Otherwise, so awesome. So I'm going to give this talk, and part of the, when Quinn asked me, if I can talk about something, I sort of want to pitch this. I'm sort of using this as, we don't have a class, at least in the CS department, on computational geometry. So I'm trying to think, okay, if I was going to build a course and have a first lecture, this is what it would look like. And then this summer, I'm pitching this as an actual course. We'll see if it comes alive, and if you enjoy it, maybe we'll actually have a course. And it'll probably be online, so if you're away on co-op or whatever, you can take it or sit in or whatever. So hopefully this gets you interested in the field. And with that said, I'll go ahead and just kind of dive in. I think you've seen the abstract and what was sort of interesting, or what I'll talk about. But again, today's just going to be a survey of computational geometry, just to kind of show you the interesting parts where computation is used. My professional background is in computer graphics, so I'll definitely come take that with me. But you'll see how I sort of apply it to what my bias is are introducing computational geometry. So as you folks know, when you have a subject, that means, it's a lot of things. So that's the first goal. I didn't add it here. I should have. Second goal is for pizza. Feel free to just walk down and grab a slice at any point too. I won't be bothered. I'm tempted to do the same. It smells so good.
Oh, we definitely accept have had a pizza break mid-sentence.
Oh, okay. Good to know. If you check my website, the other reason you got to go there for the slides, of course. See if you can find my link to the art of pizza. I'm a pizza connoisseur. Anyway, with that said, let's get into the computational geometry part of it. So as you can imagine, we're going to be talking about shapes, these types of things here. The Wikipedia, page actually provides a pretty decent, definition of what this is. So just, from the first sentence, it's a branch generally found under computer science devoted to studying algorithms in terms of geometry, working with geometry, shapes, and so on. Oftentimes going hand in hand with computational geometry is computational complexity. So for CS or math folks who have taken theory or algorithms course, that's a big part of what folks actually study in computational geometry. I'm going to be showing you some very pragmatic algorithms, but geometry is very much something that you can just sit on the theory side, or you can go more on the in practice side and have a career in either direction. So the actual origins of computational geometry, this has a pretty long history. You can go back to, I don't know, thousands of years, right? As long as geometry's been around, which you folks probably know better than me. But the sort of coining of the term comes from this gentleman here, Michael Shamus. His thesis in, I believe it was 1970 or so, is really what folks use as a baseline, right? This is the first sort of applications in computer science. So you can click on this link, you can actually check out the thesis. This may be interesting just for you folks to check out too, just to see what theses look like if you're considering honors theses or these types of things, depending on what branch you're in. But then there's a few other sort of seminal papers that capture the actual field that I've listed here. So these Voronoi diagrams, which I'll talk about, maybe I'll mention at the end. But anyways, fields where computational geometry is used, if you're interested in robotics, so sort of motion planning, finding shortest paths, these types of algorithms are where things tend to show up. GIS, information systems, usually concerned with compressing or how to store lots of data, geometry about our actual world. And then, the two I know a little bit more about, computer aided design, so CAD, sort of doing 3D modeling, these types of things, and then of course in computer graphics. So just kind of surveying around here, I'm trying to see how many folks have done computer graphics. Handful, some folks, I recognize from class. Has anybody ventured into 3D modeling or stumbled onto it? Yeah, you should try it out, it's kind of fun. Okay, another handful of folks. So yeah, those are the most sort of obvious, again, applications. There are more though, if you get into, and by molecular modeling, we mean actually like biological applications, protein folding, these types of things. Northeastern does quite a bit of work. Even circuit design, right? Circuits aren't just a bunch of transistors laid out in a nice grid. Sometimes you have to design them in different patterns. That's getting sort of into the physics of it, but because we can't, if you put things too closely together, that's sort of a problem. But also if things are running sort of in parallel to each other, that's also a problem. So there's all sorts of interesting applications. And some of the algorithms in computational geometry actually apply to other things too. You wouldn't expect like database searching and so on. So interesting field, quite wide. But today, I'm going to focus a little bit more on a problem in computer graphics because again, we can see it. So I think it's kind of nice and it's fun. And like I said, my bias is, computer graphics. And if I have a course, this is the kind of stuff we're going to do. And we'll pay a little special attention to this problem of collision detection. So two pieces of geometry and trying to figure out, how they collide together. All right. So specifically, that's sort of, this field of computational geometry is related to an actual physics engine. So again, if you play games, you might care about this problem. If you watch movies, enjoy Pixar films, kind of care about this problem, right? You have to sort of simulate a realistic or cartoonish environment, depending on what the theme is, but something that's believable, okay, or obeys some laws here. So, computational geometry really fundamental to this problem, right? You have this giant, I guess it's a skyscraper, looks like a Jenga tower to me, but sort of an extreme Jenga. But this is the type of for a physics engine, there's really three components that are taking into account the different things in computational geometry. So just to go through these three components, and then we'll look closely at collision detection here. The first is really this idea of integration. So just how do we move things? This is probably your physics, I don't know the number, but whatever physics 1 is, the first physics course, you take that equivalent, maybe some of your calculus, doing derivatives, these types of things. Right, we got to move stuff around. Then the second part, the fun part is, well, we got to detect when things that are moving around, when do they collide? So we need, this is going to be the central problem we look at in a few moments here. Collision, and then finally the resolution here. Okay, so we've detected there was some sort of collision to objects, and this is where we sort of follow Newton's laws or these types of things here. You gotta figure out which direction were these objects traveling and where do they bounce from. Okay, call this resolution or the response stage. All right. So that seems like a reasonable way to sort of break this system down into three parts. But again, as mentioned, the collision detection, that's sort of the interesting one for today to look at. So let's go ahead and give you a little problem here. So what I've got here is a bunny. And there's a specific reason it's a bunny, and I didn't choose any particular other object. This is called the Stanford bunny. It's famous in computer graphics. That's your default model that you use to test sort of computer graphic systems out. We do, if you take my graphics course, someone has made a husky as well. So well, we will try to popularize that as best as we can, starting with assignment 4 coming up soon for my graphics students. But anyway, we have this this 3D object here. So again, you can tell it's computer generated. It's not a real bunny. Don't worry, no bunnies are going to get harmed today. They are going to collide with each other in some way. So the first kind of question is, how do we represent this object in 3D? Okay, so this is part of computational geometry. So this is what the bunny looks like without its fur. So that is sort of taking up everything here. So what you're seeing here is a wireframe of the bunny. Okay, what we'd call it, or at least the wireframe part is the individual, what I'll label in a moment, vertices, and then the edges, the lines between them. Okay, and we call this a 3D mesh graphics. Okay, so that's the actual geometry for this object. Right. So again, depending on your background, again, I'm looking at this as a sort of computer scientist. So when I see this bunny, I also think of it like a graph, essentially, right? Made up of these red dots here. Those are the vertices, and then the blue lines, I've highlighted a few. Those are the edges between them. But if you're coming more from artistic background, you just refer to those as the edges, individual faces, or so on. Okay. But again, I might label something like this. This is how you'll see it in computational geometry as a graph with some amount of vertices and edges. Okay, and then I think for folks who have made it through algo, right, you learn about how to do different traversals and sort of travel through these types of graphs. Same thing applies here, computer graphics, geometry, and so on. But the important insight here is this idea that this mesh is actually made of triangles. So if I kind of stare at this, and if I look enough, I can see a triangle here. And I like to give, I can dig a little bit deeper into this, but I know I'm at the math club today, so I don't have to probably define triangle, and we sort of intuitively know what it is. Although it is proper, it is useful to have definitions. So I'm going to show a few definitions to get us on the same page here. A triangle we will accept. So a little bit here on polygons and triangles here. So again, a polygon, as you might expect, is what we're going to work with in geometry. So again, you folks have seen this certainly somewhere, depending on your career, certainly in school, different types of polygons, triangles, etc., with different classifications, right? They're regular, irregular, etc. But I do like this triangle over here. It's nice and simple to work with here. And again, different classifications. I just thought this was a nice chart for completeness on this slide set here. But there's really two types that I want to work with. Convex polygons and concave polygons. Okay, so they're just sort of interesting as far as these classes here. There are equilateral polygons, or I just call that a quadrilateral or a rectangle. It's fine as well. But different ways to classify things. But let's just look at this concave and convex polygons here. All right. So of course, when you learn about these things, the sort of definition of, I started looking at this and I said, okay, I'll go to Wolfram because it's a pretty, authoritative source here. So a concave polygon is a polygon that's not convex. Okay, sure. But again, just remembering back to your geometry days, we're thinking about the actual angles, the interior angles to determine what's convex or concave. So better maybe definition. A simple polygon is concave if and only if at least one of its internal angles is greater than 180 degrees, something that's spread out really wide. Okay, an obtuse angle has been found here. Okay, something greater than 180 degrees. So convex would be the opposite of that. Okay, so you've got this here on the right side. All right, so this is where we start from our computational geometry stuff. But when it comes to computer graphics, as far as I'm drawing these things here, if I was just drawing this on a piece of paper, it's kind of nice here. It's no problem as far as, again, just drawing this. But again, we have to sort of do this from a graphics or algorithmic standpoint. So there tends to be a preference for convex polygons. Okay, and I'll try to describe why that is, maybe some properties we can use for this. It's not that it's impossible to do one or the other, but we like convex polygons. Okay. So again, another definition of a convex polygon, but just sort of, again, diving in a little bit more than a convex polygon is not just something that's concave. We sort of like it because I can take, pick any one of these points here and draw an edge and connect it to, another side. Okay, so we'd say it's sort of, I could take any point or any one of the vertices and connect it to some other vertex and have a line segment there. So that's a nice property if I have that. It ends up making things a lot simpler for the problem we're going to solve with collision. And recall also that, if I'm an artist making these 3D figures, a bunny, for instance, that's quite complex, and I want to get it to something simple like a triangle, it turns out that triangulating a convex polygon is essentially trivial. Okay, so let me just draw folks' attention to the top right here. Right, you just pick an edge, or excuse me, a vertex here. Let's pick P0, and you just connect it to every segment. Then we've broken that this polygon here into triangles. And then triangles as simple as we can get, so we like that. Concave, we actually have to think about it a little bit. Again, algorithmically, maybe I just happen to pick this one here, and I say, okay, I'm going to try that same algorithm where I draw to all the other points, and whoops, I can't triangulate this. There's a hole here. It's not connected, or there could be a hole. Sorry, I could have a hole here. So, it's not that it's impossible. Clearly, you can see that I broke this concave polygon into triangles. I just have to think about it. Okay. So when it comes to computation, more thinking, more instructions, that costs us speed and time. So we like this. We like these convex polygons here. All right. In this general problem, again, just to give you the landscape of what we have here, this is just called decomposition of a polygon. So taking a polygon and decomposing it into some simple primitive, usually a triangle. Okay, and there's different. I'll move one more slide here. You could have said, "Hey, I have this polygon here." I could have picked, any one of these vertices to start from, and you do get different triangulations. And for those of you who want to go on and do some research a little further into this, there's different properties to having different triangulations that might be nicer or not. Yeah.
I'm currently studying the relationship between different triangulations of polygons
Yeah.
using cluster algebras.
Oh, very cool.
Yeah,
So, you probably know more than me.
it's just that there's a certain type of algebraic object created by taking a polygon's all of its possible triangulations and as a graph.
Yep.
Where they share an edge if they can be achieved by taking the flip of a diagonal across every quadrilateral.
Yeah, very cool, very cool. Have you found, so in your research, are you trying to apply this to any specific domains?
Well, actually, it was being applied to triangulation of surfaces like you saw with the like wireframes.
Okay, cool. For better, I guess, rendering or something like that?
Well, it is for the math side of the research, so it's more on the theory.
Very cool, okay. Have to come to computer graphics, we have the same graphics. So yes, evidence, let's see, I don't have anything to give you other than more of your own pizza. But this, so as was stated here, this is the whole, I've got a wiki page here and you can look at all the different methods. You can talk to your other colleagues here, whole research area here. There's other sorts of reasons you might want to even, so triangulations, super important. There's also breaking things into quads or sets of 4. That's sort of nice because those types of shapes animate a little bit better. So there's all sorts of stuff. I've got a YouTube video you can check out later on this. All right, so that's on triangulation. But let's get back to our problem, right? I'm trying to just get these two bunnies to collide with each other. Okay, sort of our initial problem here. So I want to just detect, hey, I've got this bunny made up of a bunch of triangles. Did it collide or crash into the other one here? There's the bunny here. Okay. Gotta love these animations here. But you can kind of see, and I've highlighted it here, where it's intersecting. I know it's a little bit of a weird picture, but just imagine our first bunny there. You can see it's intersecting with this one right here. Okay, so they are colliding. If I just, gave you this information, how would you, what would the algorithm be? What would you do to sort of test just if some collision happened? And, put yourself in a sort of, you're in a game or something, you just want to know. I saw firsthand here and then here as well. Yeah.
When you go through all the points or vertexes, see if they either overlap or they cross where they're supposed to be, or like boundaries.
Yeah. So iterate through every triangle, test if there's, at least one that intersects, and there must be some intersection. Yeah. Follow up here. Sorry. Right behind, and then I'll give you the next.
I basically was thinking the same thing, but I feel like if you know sort of where they're planning on going, you restrict your check to the ones that are closer together.
Okay, yeah, so if I know the direction, if I know, something about the orientation, maybe I can just check like this, a few of the triangles, yeah, okay, I like that, and yeah.
I specifically test if a line segment of one passes through a face of the other, a triangle of the other.
Yeah, so I can pick, so specifically picking one of these segments, we've got I mean, this is just a line segment triangle intersection test, which if folks want to come take a ray tracing graphics course, that's exactly what we do to sort of draw these objects here. Okay, so I like these ideas. Any other strategies? All are correct, right? Well, we will be able to detect some sort of collision. I have, let's see, let's see, there goes the bunny again. Come back. Oh, now it's totally gone. But you know, the very first thing, so again, you know, I've got to start bringing chocolate or something to give to folks, but yeah, you know, first try to do an intersection test between every single triangle. Just kind of look through every one and do, you know, we can sort of, this is going to be the thing that you folks are probably better than me, right? Take two planes, see if they're intersecting, right? If there's some line segment. And then you kind of also figure out, hey, this is a triangle, so there's some point fit in there. I think we sort of get the idea. All right, let's see how many times we're stuck in a loop there. So we do have to talk a little bit about intersection of geometry here. And I'm just calling this, you know, the triangle to triangle intersection test. Exactly as your colleague said, to test if these two bunnies are colliding, essentially just loop through every triangle. Say, hey, I'm going to start from, you know, the bunny's nose, and then test against this triangle, this one, this one, this one, this one, this one, this one, and see if there's some intersection that occurred. Right. And for my algo folks, you could probably say, well, you know, this is some sort of n squared test, right? So if the nose here didn't collide, then you got to do the next triangle, then say, okay, did it collide with this, and you go back here and you say, okay, the next triangle over to collide with this, et cetera, et cetera. So this kind of takes a long time. We have to do this sort of test, which, you know, fine, maybe. You know, sometimes we want that precision, right? If we're Pixar or something and we have infinite time, right? When you watch a movie, you don't care how responsive. It's just showing you images. Maybe that's fine, but you know, we probably want to do something a little bit faster here. Okay, so let's still hold on to that idea though, about just sort of testing every triangle doing this sort of intersection. So there's this separating axis theorem, which have folks seen this in maybe a geometry course or anything? Maybe not. Well, I can give you the definition because it's right here. But the basic idea is I say, okay, here's two, you know, and sorry, I haven't defined this term, convex polyhedro. That's what the bunny is. It's a 3D mesh made out of a bunch of other convex shapes. Okay, so the bunny itself is convex. Okay, and basically the idea is if I take all the individual vertices where they are in 3D space, and I project them onto some axis. Right, so in 3D, I'm going to need a x-axis, a y-axis, and a z-axis. Well, then I can just sort of test if those points overlap at any region. Okay, does that make sense to folks? Maybe just looking at the diagram, you kind of say, hey, in one dimension, I'm just going to say, you know, the leftmost vertex of this thing over here, the rightmost vertex of this thing over here, and do the same here. And if they overlap, they must cross each other, right, at some point here. Okay. Now I do need to sort of do this, you know, for every single vertex in my bunny, sort of projected onto this line here. So again, this seems fine. Okay. And let me also, so folks okay with this idea here? Yeah, question.
So you're projecting the, like in 3D, take the 3D example is you're projecting it onto a plane, and then if any points on that plane have to be like overlapping or have to be separated by a plane for the two convex polyhedra to not be colliding.
Correct. Yep. And we do need a little bit of linear algebra for this to work. This is called a projection. I take something from maybe in this case, since I've got a two-dimensional figure here, let's just focus on this circular shape and this pink hexagon here. Right, and then I can project it. Projection takes me down one dimension, so I'm just on a line here, on a number line, kind of seeing if numbers overlap. Okay. Yeah.
How do we find the separating line? Because like, doesn't that sort of assume that they like aren't colliding?
Yeah. That was something I was gonna skip. Assume we have this line here.
Okay.
Yeah, because we have to figure out I mean, at the very least, right, we have this axis, and there's a way to get this sort of what we call a sort of axis aligned, because I sort of know the orientation of the bunny. It starts in sort of a default. Sorry, I do this in my graphics classes, the right hand rule. But I'm sort of in a default orientation, like myself here, I'm sort of flat on the ground. I sort of know if I rotate it or something. So I know sort of this axis I can project points onto. Now how I get this magic line, at least for now, let's just not worry about, let's just say, okay, do any of these points overlap here? Yeah.
And when we project a 3D object onto a plane, it has to intersect in each dimension in order for that to actually
Correct.
get
Yes.
to intersection. So we have to
Right.
test it in multiple projections then, right?
Right, yeah, because we can sort of do this experiment. So if I just look in one, right, so if I line myself up, we'd say, oh, we're, intersecting. If someone's just like looking, from behind one of us, but obviously somebody could walk or pass through. Yep, 100%. Yeah, so we at least know we have this test we can do, right? Does this make sense for folks? Yeah,
I think you said at some point that the bunny was convex, like a convex polyhedron.
Yeah.
Why? Because
why?
like there's definitely points in the bunny where I can imagine something sticking in there and like projecting it would be overlapping, but it wouldn't actually have collected.
Yeah, basically, let's see if I can draw it here. I draw, so I guess I could just draw with a cube maybe. Let's see. All right, let me give this another try over here. More folks can see. We actually have another tool to help us with this graphic. So we model something called the normal, which is again, same mathematical definition you learned from a plane that's projected perpendicular to each of these edges. So as long as for each of these neighboring faces, the normals are pointing out away from each other, it must be that they're not caved in like a concave shape, so that that angle that's formed with them can't be obtuse.
So we're calling being convex a local property then.
Yes, and it must be true for, if it's true for these neighbors, in those neighbors, it's true for the ones.
It doesn't have to be true for like pairs that are far apart.
That correct, yeah. Yeah, so the tail versus the nose of the bunny, for instance, I guess it could like wrap around like.
Because like
this
the ears
or
face
something.
each other, but that's okay.
Right.
Because they're
Yep.
not.
Yep, correct, yep. Yeah. So yeah, that's kind of, I have a little slide, I can try to find it again, also defining that term, but that's the idea. I guess the other important property for this would be, maybe an easier way to define it is if I had a donut, for example, that has a hole in it, so that's definitely going to be a little bit problematic. Okay. So that would be an example of not convex polyhedron. Right. And then just to reinforce again why we like convex shapes, right? If I have a bunch of convex polygons mixed with ones that are concave, this sort of nice clean axis doesn't work, this sort of test, because you have something that sort of wraps around. So we don't like that, okay? that breaks this separating axis theorem. Right? And then this is my note here. We need to do this sort of projection to go from 2 dimensions onto a number line, or from 3 dimensions into 2, and then repeat that process. All right. So, again, this works. This is totally fine. But I'm a little bit concerned with the amount of computation we're doing here. And I'll tell you that Bunny has 69,451 triangles, which I don't know if that gives you a reference point, but I'll tell you that's a lot. Okay? If you're trying to process, a video game or something that's drawing maybe a few million items, you can't spend all of your triangles on the bunny. Sort of say it that way. Right? This is a big enough or complex enough shape that we need a faster test here. As was given by your colleagues over here, and it was already stated that one of the other ways that we could test for a collision is just say, well, let's just, maybe use some information we have. We could either just one side of the bunny or maybe just approximate if a collision happened. Okay. So how could we approximate a collision with two bunnies? Let me ask this a different way. Are there any simpler shapes you can imagine using to test if a bunny collided with another bunny that might be cheaper or faster to compute? Yeah, spheres. A sphere, yeah. You just kind of approximate the bunny with a sphere and say, is this sphere overlapping?
If nothing else, it would at least give you a region in which they would intersect.
Yeah, and it would at least tell us, is the test worth having, right? If we at least use a sphere. So this is something called a bounding volume. See here. So the answer, use simpler shapes. And let's go with spheres here to start. Okay. So we could, again, as mathematicians, right, sort of figure out the leftmost point, rightmost point, bottommost point, topmost point, and then point out to sort of figure out what's the radius of a sphere that's going to tightly encapsulate this bunny. Okay, so I can fit this bunny inside of this sphere. Okay, and then you can just kind of use that information and say, okay, from the middle of this sphere, I know the radius, and I know the middle location of this sphere, I know the radius. And if let me use my cheat sheet here. If I add the radius to those spheres and they end up being less than the distance from the center, they must be overlapping. Okay, at least the spheres are overlapping. Okay, so that's a technique that games, physics simulations will use to approximate these two shapes colliding. Okay, so this works. So we call this generally a bounding volume. Okay, so it's the sort of shape that encapsulates the bunny. Right. Folks, okay with that? All right, awesome. All right, so there's many types of bounding volumes you can have too. Spheres, the simplest, it's the fastest, that's usually the go-to. But you could use boxes as well. And there's different types of considerations you'd want to take as well. Does the box align with the object as they turn, or is it just a box that surrounds the object? So we have different names for these things, axis aligned or oriented bounding box, etc. Folks tend to use capsules a lot. So imagine like a pill or something and sort of putting an object there. So you can sort of, again, that might be a little bit of a tighter bound for the bunny. But what's the trade-off here with using this simple sphere versus our triangle test? Yeah.
The more different or the more extra space is included in your simple shape, the more likely you have a false collision.
Yeah, right. So I can kind of see, right, look at all this kind of wasted space here. If this bunny was, approaching this other one, we're going to get a false positive here, right? It's going to say, yeah, there's a collision. And again, depending on your simulation, maybe that's okay, but we probably want to be a little bit more precise here. All right, it's a trade-off of precision, versus our speed of detecting a collision. And as was mentioned, usually we combine both of these. So we would have sort of a sphere to do a quick test, and then we maybe are then going to spend the time to do the triangle test. But there is something in between that does a little bit better, and this is the idea of a what's called a convex hole. Okay. So just to illustrate this, I'll define it. Let's imagine I have this bunny here, and I'm able to figure out a tighter bound, some other shape that definitely encapsulates all the bunny that's fully surrounded here. But it seems like it's a lot more precise, right? I can get a little bit more of an outline here of this shape here. So this is what I want to talk about, and this is, sort of the use case of computational geometry. So what is a convex hole? Well, it's the smallest convex set, so some set of points here that contains all the vertices. Okay, so the way to just say that is it kind of wraps around the object tightly. Okay, and I'll give this a name. I'm trying to walk carefully without giving a surprise here. but again, we can see this seems better than a sphere, even for this complex object, right? There's less sort of wasted space here. Okay, and you could actually measure this volume and try to figure out precisely how much you're saving. But before I give you a solution to this, and you can study this if you want to see the actual algorithm in progress. How would you intuitively build this convex hole around an object? What do folks think they would do? I'll give everyone 10 more seconds. I saw here and then here. I could try to think about this, or maybe just kind of study what's going on in this picture. It gives you a good idea. Let's see, I'll go here.
It's kind of what this algorithm is doing, but you would scan until and you hit a vertex that's furthest out. Because if you go any further and there's no other vertices, you can stop there and make a plane and separate from the outside from inside.
Yeah, okay. And yeah,
I mean, that's essentially similar, but I was thinking, like, go as far out and then go in. So like, get a plane that's sort of tangent to the point, and then scan like up a bit on each side.
yeah, but both right, both saying this, the right thing in different words. Right, we could kind of study this diagram, what this is doing here. Right, we're kind of, we need some starting point. So usually we look for an extreme case, right? A point on, the far left, the far right, top or bottom, which you're both mentioning. And then we've got to kind of look at, what's the point that's going to, encapsulate or maybe separate, where we have all of our other points on one side of the edge and then nothing on the other. Okay, so we can kind of see that's what's going on. And that's what this is doing. This is scanning literally all the points here, but it's saying, hey, if I happen to choose this point here, I'm looking through all of them. Is this, and you're gonna have to, I'll have you turn your heads in a moment, are all of my points to the right or left, depending on how you build this, of this particular point? If it is, that must be part of this convex hole. That's a vertex that we care about. And if you can imagine shrink wrapping, your object, it would tightly surround it.
That would also be how you select your starting point then, right? You would pick one that can be separated as the only one on the side of a plane.
Correct, yep. And we can sort of do that by just, usually the folks do that, so they just say, all right, what's my furthest right point or left or something like that. Yeah, because then that must be a starter. There are a little edge cases too, if you happen to have a bunch of points that are like in a line or something, but let's ignore those edge cases. They're somewhat trivial, right? You would just say, what's the minimum? Pick one. So again, a lot of times folks, we like to visualize this again, if you have like a, what do you call it? One of those boards where you put the tacks in or whatever. And if you just stretch a rubber band around all of these thumbtacks, right, the rubber band's gonna snap, and that's what's gonna make the actual convex hole. So given more time or your next math club activity, right, we can build convex holes if we get enough thumbtacks. Just throwing ideas out there, some good, some bad.
I have an idea for our holiday social. Next gift, you know what we're doing.
Yeah. And this has a name for it. These are gift wrapping algorithms. So think about this for the holidays also coming up. So where this comes from, way back, or actually not too long ago, I suppose, but 1973. So that's old in the field of computer science. For mathematicians, this is like, new age stuff.
Modern.
I don't see Archimedes on here, I think. But again, yeah, this is the idea right here. Picking a point here and then randomly choosing this and saying, okay, if I choose this point here, do all of my points fall to the right of this segment? If so, proceed. And you can kind of, keep repeating this test. You've got to, turn your head as you wrap around this object. But that's the idea of gift wrapping here. All right, so you can try to convince yourself. Yeah.
Do we have to check all points to guarantee that they're all to the right of the line segment that's created?
We do in this algorithm called the Jarvis March. We do. Yeah.
Okay.
Yeah. So we would say, and we could probably pick somewhat intelligently, starting with some extremes and that sort of marking them as, not interesting. The reality is this one's going to be, I'll show in a moment, at least O of n, because we have to look at everything, we have to pick everything. And then how many points we have in our hole, which we just call H. So, I mean, it could gear towards n squared-ish looking. The reality is though, there are better algorithms, but this is the Jarvis March, which I think we can understand in a minute. So here's the other ones here, just to, questions leading me to, slides. We get down to n log n, it's pretty good. There's even ones, and you probably don't see this in your algorithms class, but are interesting to think about, that are O of log n of log n, so they even do a little bit better than that. So this is still like an active research problem if you can solve it, or find a specific case where something works best. Most folks are probably looking at this one called quick hole, sort of like quick sort. That's just sort of a default. This is a good one to do. But regardless, what this class of algorithms is doing is just wrapping your shape up and creating this convex hole. All right. So here's an example, as I showed before, of our bunny. Again, gift wrapped nicely here in their package. And again, just for comparison, right? Our convex hole versus the bunny, right? There's less volume total here versus this shape, all this sort of wasted shape. Okay. And then the other thing to observe is now that I have this convex hole, and again, sorry, this is a kind of grainy picture, but you can at least I guess I'm not lying to you to say that this convex hole is this is not 69,451 polygons. This is maybe 100 or 200 polygons, something more reasonable.
So we like working with convex shapes, convex polyhedra for collisions.
Yep.
Is the hull here like the optimal shape then? Because you can't make a smaller convex shape that would still get to your points.
Yeah, I think in that case, that's true. Yeah, I don't think we can do any better, or at least that I know of. I'm trying to think, because we can sort of see like, hey, we pick this, bad edge or vertex here and created this edge. So there is wasted volume here, but
If we made it any smaller, it would be concave.
then it's going to get concave. Yeah.
What's the definition of convex?
It is, yeah. If I go back to the definition, right, these small is convex, so it is a minimum. Yep. Thank you. All right, so here we are. And then, with this convex hole, we can do other sorts of things like, if the body rotates, we rotate the hole with it. Again, we get this precise sort of collision here. All right, so again, now we can go back to our this separating axis theorem, and we don't have to compare 69,451 triangles with this one, right? We can sort of do this quick test with maybe just a few hundred vertices that we're projecting on a line and get something, super, or I shouldn't say super, but more precise. And again, something that's going to be easier to work with. We also want to use this convex hole for other things. I forget what this is a little bit sad, but you can imagine a bunny rolling down a hill or something. It's just spinning, having fun or whatever. It's going to look a lot more realistic if I sort of use this convex hole to model this shape. That's not going to be, perfectly a circle or a box, right? If I'm just trying to model that behavior. So no animals were harmed in the making of this presentation. All right, so that sort of gets us to it. All right, so wrapping things up here, source. In summary here, we're about at time. We've looked at just some of the fundamental primitives, these things that we learned about convex versus concave, specifically the triangle. The triangle also plays a really important part of just graphics for how easy it is to draw something. We've seen some of these primitives and how we could use them to build something useful, hopefully useful. There's lots of things to explore just from this presentation regarding how do we even represent this mesh or the whole as far as the actual geometric data. As was mentioned, the different types of triangulations that we can do for data. Didn't talk about numerical precision and these types of things. Important, not really a computational geometry thing, but important in computer science. Decomposition, and then other sorts of interesting things like constructive solid geometry. That's what this picture is here, where I'm sort of taking some of these primitives, taking their intersection, and that gives me a primitive here. You kind of walk through this graph unioning, so I get this sort of shape that I combine these two, and then forming other objects. This is something you might do when designing or modeling a 3D object. And then there's other sorts of things in geometry, like motion planning, finding shortest paths, these kind of things, right? This essentially we're traversing graphs. So this is just sort of a for fun thing. This is where a lot of courses usually start off in geometry. That's something called the art gallery problem. Has anybody heard this problem, or some head shakes, or? Yeah, okay, so this, I'm gonna leave it as a video because they do a nice job here if folks want to check it out. But again, if you're sneaking around an art gallery here, these two guards aren't very smart, I suppose, but you know, how many would you have to place such that you couldn't escape the gallery with any artwork? Something fun to think about here. So with that said, we're right 2 minutes past, but thanks for having me, Math Club, and I'll stick around for a few questions or whatever. And I think there's still pizza there. I can see some.
That's also for you.
Sure.
But you folks go as the pizza connoisseur you are.
Yeah, I know. I'm looking at this. Nicole's haven't had it, so gotta leave a review. Any questions for the group from folks?
So when you have the convex holes and you check for intersection, would it be better to use a more naive way versus utilizing the separating axis theorem by that point?
Potentially, yeah, we could probably do better. So
It sounds like using the separating axis theorem is expensive, since you have all these different projections you have to worry about, 3D space at least.
yeah, it's expensive. I guess the good thing is it's highly parallelizable, which is good. So it can sort of terminate early as soon as we know we have an intersection. Yeah, we could probably do better. Yeah.
How does this kind of process work if your object isn't rigid?
If it's not rigid, that's a good question. I was thinking about this a little bit. So a rigid body would be something that's not deforming, right? When we sort of collide in the real world, right? Bunnies, right?
The bunny rolling down the hill is going to move.
Yeah. Usually we model things as sort of springs. And then since it's deforming, I guess, I mean, that might be a case of,
You just like check its new triangulation at each frame.
yeah, essentially, which is expensive. That's why you don't tend to see it as much. Not that it's an impossible problem though. If folks want, feel free to email me or whatever. I've got a really good talk showing like cloth and deformation and stuff. That might be fun to watch. Yeah, Quentin.
Do you have any recommendations for, I guess, external sources? I know you show a bunch on there, but for computational geometry.
Yeah, the main source is there's this book. It's called Computational Geometry in C. It's like 20 years old, but it's still like the book. There's that one, and then there's another one, which a long time ago, or it's not as old. It's by DeBerg. Is their last name? I forget the first name, but the name's two of the same authors, and it is called Introduction to Computational Geometry. Same as this talk here. I'll add this to the end of the slideshow. Intro to CompGeo, as well. I'll put a little resources slide for this. This is the book that my professor told me that it was so good when I was first going to read that you could just curl up on a nice Saturday evening and read it by the fireplace because it's that readable. Yeah.
What is an efficient memory representation of the points and edges?
That's a good question. I've got one here that we tend to use here, some sort of index list. That's okay.
Do you care about like the cache, whatever, like keeping close to it in the memory?
We do, yeah. We try our best. On the GPU, we don't get as much control, but we do try to still on the GPU position things closely as well. GPU, well, we get more by using these types of things like convex holes, to be honest, versus trying to have locality on the graphics card. So the graphics card is more of just a off to the races, let everything process. There's just a little bit of cache. So I don't know of any, I guess I haven't run any experiments that prove otherwise.
So when you test collisions, is that logic being done on the CPU or GPU?
On the, like, we could do both. You know, I can compute a whole, and this is, I'm gonna give you two things here. So one is, we do have to use something through GPU. This is general purpose computation. So if we can get the data and the representation, basically get a graph of our object on the GPU, then we can sort of do a test. The problem is reading information out from our GPUs because they're really good at showing images. And why it's a struggle is our GPUs, we pay some cost to put information on it, let it compute, but then we pay cost every time we bring something back. So it can be done, but it's not clear if it's useful.
So
or
if
working for it.
If like one test like collision to like do video game logic, if you do a collision test on a GPU, it's hard to read, get the results back in a useful way.
Yeah, I mean, there's a mix of folks will do it on CPU or GPU.
Like in a triple A video game, you'll probably be using both, no one preference for the other.
Yeah, I mean, on the, depends on a console and stuff, like, you know, for a while, there were actual physics compute cards you could buy, or maybe like, I don't know, 2012 or around that time, like 10 years ago, maybe, that they would try to do this stuff. It ended up just all getting offloaded to the GPU. So, you know, in reality, a lot of it's still being done on a separate core on your CPU. And the second name I wrote is this guy, his name's Tom Forsyth. He talks a little bit about, I'll put a little reminder here, locality of your vertex data. So you can kind of take a peek at that if you want to read his sort of inconclusive results. He thinks he's sped stuff up as much as possible. He's an engineer at Valve, so he knows what he's doing. Yeah. Good questions. Yeah.
So I'm thinking about like if you have objects that are moving and you just want to see like when they collide, how would you do that? I would assume you would like process it in terms of ticks and every tick check if they're colliding.
Yeah.
And then my question would be if it's moving very fast, could it potentially jump over an object where it's not colliding in either tick, but it would have collided in between?
Sure could, yeah. So this is a classic problem, right? If something's moving really fast, like somebody throws a baseball, right? It's possible, right? If you're just checking incremental steps, right? This is where the precision comes through. So we're saying, hey, update the game every millisecond. So you say, okay, 1 millisecond, and then it jumps 1 millisecond. It's possible if an object's thin enough, or the hole or whatever, it just goes through.
You also try to somewhat correct that error by doing like trace a line and then extend the object along that axis and see if there was any if there be any intersection between the extended objects.
Yeah. So yeah, that's the other thing we could do.
Because like the baseball might skip through someone, but a cylinder wouldn't along the axis it was traveling.
Yeah.
My question would sort of be like, could you somehow treat it as a 4-dimensional object with time being the 4th dimension and see if the 4-dimensional objects intersect?
Yeah, you could. So like the bunny example of 2 objects colliding, right? That's sort of 2 holes. Maybe they're moving at a reasonable speed or whatever. They've got a thickness, but yeah, if we're modeling like a projectile or something, we would actually just treat it as a ray and then just test if any point along there. And that is a ray plane intersection test or ray triangle test. Yeah. So yeah, depending on the object that we're colliding with, we might choose different options. Because yeah, these don't have to be exclusive. I say for every object generate a convex hole. Yeah.
Maybe instead of 4 dimensions, you can still do it in 3 dimensions. You just have the object, but have it stretched a bit. So you have like this cylindrical thing now. Just compare if they collide.
Could do that too. Yeah, model as a
Of course,
cylinder.
one object is moving and the other is stationary, but then if they're both moving.
And there's something that says, you know, that the object that's moving, right, its collision, you know, thing, its whole could be also, transforming, or if it's stretching, or
Relativity says only one of them has to move, and you can pick the right frame.
Check.
There it is.
But yeah, this is hitting right on the numerical precision of objects jumping through others. This is a common problem. So oftentimes, again, in your game, your physics engine might be updating actually faster than what you're drawing because it's got to check at a faster time step.
It's the floating point intervals.
Yeah, whatever the smallest epsilon is for your floating point. Awesome. Well, this was fun, folks. Thanks for your time and attention on a Friday night.
Stop recording now.
Okay.
Let's.
This is how math students spend our Friday of Halloween weekend.
Yes. You know, in grad school, math was the most active